So in this video, we're going to look at the divergence theorem. Let's say that E is a simple solid region, and let's say that S is the boundary enclosing E with positive outward orientation. Now, if F is some vector field whose component functions have continuous partial derivatives on an open region, that contains E itself, then we say that the surface integral of the vector field F dot ds is equal to the triple integral. So basically, the divergence theorem connects the surface integral to a triple integral. So let's look at this, how this works in an example. Let's look at this example. Compute the flux of F, the vector field, through the surface of the solid bounded by. So in this example, we're going to try to compute the flux of F. And remember, the flux of F means that you want to calculate, in fact, the surface integral, S, where S is this surface that's bounding the region E. Okay, and so what we're really trying to do is this is what we want to actually compute, and we're going to use the divergence theorem to do this. And I'll explain to you why the divergence theorem is better in this case, because if you think about this, what you have is a cylinder here. So you've got Z equals A would be this plane intersecting the cylinder, and Z equals 0, that's the xy plane, and you've got the cylinder, of course, x squared plus y squared equals r squared. Now, so if we were to think of this as surfaces, we would be talking about this is this disk S1, for instance. That would be the cylindrical surface S2, the cylinder surface S2, and of course the cylinder's bottom, the S3. So you have these three surfaces, and you'd have to break up this integral into three surface integrals, S over S1, S2, and S3. So the two disks and, of course, the cylinder itself. However, using the divergence theorem, what we can very quickly do is actually write this as a triple integral, in fact. Okay, so we could write this as a triple integral, and this triple integral is over it's basically you're looking at E is the region, so it's a triple integral over E, which is the region enclosed by the cylinder, as we mentioned in the statement of the theorem. And the connection is that you take the div of your vector field F, right, and then this becomes now a triple integral. And the triple integral is actually quite easy to work out here. As you will see in this example, the first thing we need to do is to calculate div f. So let's start to solve this, and hopefully you'll see how actually easy it is to work out. So the x derivative of the x component, so that's 4x cubed y plus the y derivative, so that's going to be negative 4x cubed y, okay, and plus 2z. So that's basically the div of this function. Okay, so notice that these two cancel, and of course all we're left with is just 2z. Okay, so that is equal to so the z, our z here, if you will notice, is between 0 is the bottom of the cylinder and the top of the cylinder is z equals a. So that's simple. We just put the limits 0 to a here. The other thing we need to keep in mind is we have a cylinder x squared plus y squared equals r squared. Now that's the double integral is going to be basically looking at that cylindrical region, and the best thing to use here are our polar coordinates. So in the xy plane, what you're looking at, because these two, this is your z, of course, so these two are your xy, and of course that means essentially you're looking at this circle with radius r. So this best thing is to use polar coordinates. So your theta will be between 0 and 2 pi, and your radius r is between 0 and capital R. So we end up with this very simple, straightforward integral. Now 2z is what we're integrating, and of course it's the polar coordinates. As a reminder, we are using cylindrical polar coordinates, so the z remains as it is. So what we have is 2z, and then we have the dz. Don't forget the r dr d theta as well, okay, for the cylindrical polar coordinates. So as we work that out, that's going to be the double integral 0 to 2 pi 0 to capital R, okay? And the 0 to a will work out to be, I'll just leave us with an a squared here, a squared minus 0, okay? And then we'll have the R and dr d theta, okay? So what's left then is we integrate this, and that becomes this. We'll get 0 to 2 pi, and then the integral of that is going to be r squared over 2. So that's going to introduce here r squared, and I'll be over 2 now, and there will be a d theta left. And when we integrate that finally, we'll end up with a pi a squared r squared. And that's basically the integral. So this is how we use the divergence theorem to calculate a surface integral using, as I said, sorry, using the divergence theorem. One can calculate a complicated surface integral. So you could work this out using surface integration. However, keep in mind that you'd have to be solving this over the 3 surfaces. Okay, and you know it's much more complicated, and the divergence theorem makes it much easier to do.